Hi, I'm Toby, and this is Learning Dart from Scratch, where I learn Dart from scratch and you watch me learn Dart from scratch. And we're up to part 2. So far we've been working on a problem where we have a list of words and we need to arrange the letters that make up these words, the set of letters that make up these words, such that the letters come in an order so that the words that you can make with the letters that have been introduced introduce themselves as soon as possible. So what I mean is, if you're teaching the letters one at a time in a series of lessons, you want to then have the words available to the students according to which letters they've learned to be maximized early on as possible. So we're ordering the letters, the order the letters get taught in, and that's the problem we're trying to solve. So far we have done, we've just got we read the file and we order the letters. We don't order them, we just collect the letters and spit them out in the output. Let's run that. So we notice that there's some letters in here we don't want. This one, ellipsis, this 3, the space, and the 1 and the 2, which are here. The one there, there's a 2 somewhere, I'm sure. So what we'll do is we'll get rid of that when we construct the word. So this is part 2. You got to watch part 1 first if you haven't. Now I'm going to do some code here which is very specific to this case. It's not general at all, and that's because MPJ says don't generalize until you need to, until there's enough occurrences of what you're doing to abstract into general form. And he's a very wise guy. If you don't know MPJ, follow him on YouTube. His channel is Fun Function. He's a wise programmer. So what I'm saying, I want to remove. I'm just going to remove those particular ones. Can I remove an array of a whole bunch at once? I'm going to list. This is the set. I'm going to set. So remove. Remove all, and you give it a iterable, which a list isn't iterable. So I will use that, remove all, and give it a list of things I want to remove. So there's a space, we want to remove the number 1, the number 2, the number 3, and the ellipsis. Copy. You know, when you copy from a terminal, you have Shift, not Control C. There's something else. You Control Shift C, Control Shift V for paste, Control Shift T for new tab. Otherwise, that's just a tip for you guys. Yeah, why is that like that? Okay, so let's save the file and try again. Yes. Okay, so now we need to actually order them. Right. The way we're going to order them, I've thought about this, and lots of different things have passed through my mind on how to do this, but I've rejected them except for simulated annealing. So this is a heuristic. A heuristic means it's an algorithm where it finds an optimal solution among many, and it's called simulated annealing. This is here's a helpful website. Hang on. And this website really explains simulated annealing quite well, quite simply. It's a good heuristic to use when you've got you want to reach this optimal point, but there's these other local maxima. These are like solutions which are adjacent to each other, which means they're quite similar solutions. And you get, if you just do like an algorithm which tries to compare similar solutions and choose the better one, then compare, you end up maybe at a suboptimal solution. So what you want is you want to be able to get to this one. So what simulated annealing does, it lets you, instead of just going up to a better solution, lets you sometimes go down to a worse solution in order to get past these local maxima to find the global maxima. So how does it work? You just you start with any solution, and then you have to calculate the cost. You work out how good the solution is. Then you get a random neighboring solution. You calculate the cost of that one, how good that one is. You compare them, and if it's better than the neighboring one, then you go to it. And if it's not better, then you maybe go to it, and you maybe don't, depending on another algorithm. Then you keep going. So what's this maybe? That's here. That's the you have to use acceptance probability function. So one thing that's important is that as you're searching, you start off there has this temperature. It starts off high and it gradually gets lower and lower. And when it's high, you're more likely to be able to move to a lesser solution. So you can be jumping around all over the place. And when the temperature drops, you can only go. You're less likely to be going downwards, and you're only going upwards. So then you'll be climbing up. So, and the acceptance probability function is e, which is the constant e, to the power of the difference between the cost of the two solutions you're comparing over the temperature. And that will give you, and then you compare that number with a random number between 0 and 1 to work out if you're going to go down or not, or stay going up. Okay, and it helpfully gives you the code. Here's in the Wikipedia article, you can see it, a little animation of it running. So as the temperature goes down, is less jumping around and staying where it is. So when it starts off, the temperature is high, and it can go anywhere and go up and down. It can get different ones, and as the temperature drops, it doesn't do that so much. So that's the algorithm we're going to do, and helpfully we've got a Python implementation of the skeleton of it. And what you've got here, you've got the temperature, the minimum temperature going to the change in temperature. So you're actually multiplying by this amount to get down, so the temperature drops slower and slower as it goes. Then for each temperature, you do this 100 times in this one. It says it's got to be like 100 to up to 1,000 times. You compare them and you get the acceptance probability, and then if it's more than the random number, you take the new solution. That's it. So you need to work out how to do the cost. You need to work out how to get your neighbor. You need to provide the acceptance probability algorithm, which it should have done because it's here, but I can write it. So let's put that in our code. Put it down here. This is put here. Okay, and now I'm going to pause the video while I convert this to Dart syntax. Okay, I've done that. And while I was doing that, I also noticed that the the Dart plugin for Atom is looking for Dartlang projects before it turns itself on, and where it defines a project if it has a pubspec.yaml file in it, which is every Dart project is supposed to have. So I will put one in and see if that helps the plugin to actually work. So I thought it was a little sparse on the ground, this plugin. It wasn't turned on. So let's just do that. No, it's not one pub yet. I don't know what, okay. And I think it just needs like a name. Something like that. Like here's an example name. Okay, I should go space in it. I need to put that. Okay. Now, oh look at this! I've got warnings. Yeah, function cost isn't defined. Yeah, that's worked. It's good. What's this? What's this? Error. Oh, this is int. Okay. I've got errors. Okay. Now this is warning. This is warning. Okay, these functions are not defined. Can I say define it? No, I can't. Okay, I'm trying to get to that would be called, this sort of thing is referred to as hate-driven development, where the IDE hates your code by giving it all these red underlines and warnings and errors, and then from that prompts you to actually write the code that you need. And if your IDE is good enough, it can generate some of that code for you, which this one is not going to. So now I am going to put these functions in. So let's do the acceptance probability function. And that returns a number. Double. This is double. Oh, look at this. Oh no, it's not gonna autocomplete that. Takes the old cost, it takes the new cost, it takes the temperature, which is also a number, and it does the thing, which is this thing here. E raised to the power of the difference over temperature. So E. What's this mean? This function. Oh yeah. Okay. Good. E. Okay. I think I've got here E constant. So in math, there's an E constant. And do I have math going? Yes. This is unused because I'm about to use it now. E. And now I want to get the power. That raised to the power function. Pow x an exponent. e raised to the power of the cost difference, which is old minus new, old cost minus new cost, divided by temperature. And okay, acceptance probability. Now we need the cost. Oh no, let's do. Oh, what's this? Oh, we haven't done random yet. Random. Okay, you don't need this anymore. Random. Random. Random next to ball double next int. Okay. Just make a. It's in the math. Okay. Which is where you expect to find it. Let's make one here. Okay. Next double. What does it tell me about? Generates a non-negative random floating point value distributed in range 0 to 1. That's what I want. Oops. Listen to that. Now. We need to find this. Okay, now because I'm not American, I'm putting a U there, and we're going to make that function. It returns a Q, and it's called neighbor. Would you be neighbor? And it takes a Q, which is the solution. And now what we're going to do to get the neighboring ones, we're just going to take the solution is an ordered list of letters, and we're just going to swap letters somewhere randomly, select a letter and swap it with the adjacent letter inside the Q. Q swap. Yeah. So let's go to Q. So to do this, so we can get the element at, we need to then take it out and insert it. So we can remove it. And there's no insert for Q. What? No. What we could do is actually just instead of swapping, Okay. We could take one out and put on the end. That'll do. Let's try that. Where's this red thing? Oh yeah, if statements need to be bracketed like that. So we want the we need the random thing to come in. So no, because it takes a, when you use next integer, you put next int and you put in the max int. Okay, next int to max, which will be the maximum int, will be the last index. Which is the length minus 1. And then we're going to remove it. But you know what? So remove oh gosh. Element at, yeah, we're going to and that's going to be the letter, and we're going to then you know what, I'm editing the actual solution, so new solution is going to look like, it's going to be the same solution, and we don't want that. We want to duplicate it first. Okay, so we're passing by reference, so when we edit it here, it's going to edit this one, which will affect this further on. Okay. I worked out how to do this, which is nice. Straight out of Sublime Text, that feature. No, we want to put the letter in. Okay. just add it onto the it'll go onto the end, the last. But so which means we don't want to take the last one and put it back where it was, otherwise we're not changing anything. So we make that -2 so we don't get the last one. And then we return. Okay, so that's how we get our neighbor. Then we need to get the cost. Now this is the interesting part. The cost is going to be, what we're going to want is the, if we count the number of words as we, if you imagine a graph along, we're adding letters to our corpus, and then up the side is how many words we can read. How many words we can read from those letters, and we want it to rise as quickly as possible and level out rather than staying level and rising later, which means the best solution will be the highest area under the curve. So that's how we're going to measure our cost, is the area under the curve inverted. Cost is so let's cost of this solution. So to measure what we actually need is the word list as well. To work out this cost. So let's get out. Right. Okay, we have to pass it all the way through from here. What's wrong with this? Oh, we need the random number coming here. Oh, look at this, getting rid of all our... So... what's going on there? Okay. So what that was. Okay, now we need to get the area under the curve. Okay, so that means for each letter I think set has intersection. Set intersection of another set intersection section. So we just, what we do is we have a set letters learned. Letters learned. Then set, yes. Then we do this. We go for each. For letter in solution. We add it to the. We add it to the. To this one. Then we go through the words. So we need to get a score. It's a score. Okay, starting at 0 for word in word list. This we check if the intersection of letters learnt and the word letters is the word letters, then we can read that word and we can add it to our score. It adds into our area under the curve. Okay, so if now this now it'll be a different set object, but it should have the same content. Now I'm wondering if this comparison here is what I want to use, and I'm so this is a language specific thing which I don't know about in Dart. Is there like a compare equals? No, which suggests that I do want to use that. Compare two sets. Oh no, they don't. Quality classes. Equals. It's not. I'm not going to listen to a set, so. contains all. Set contains all. Oh, I don't even need the intersection then. If letters learnt contains all, then we know this one, and so we increment the score, and then we want to make it a cost. So we invert it like that, and then that's our cost. That's our anneal. Let's anneal this. Is so this what we've got here. We've gathered the letters together in whatever order they come out, and that's going to be our first solution, which we're going to start with. We'll do the annealing algorithm and find the optimal solution. Hopefully, let's see if that works. So, no. What? Oh, I got to pass the words through. Where am I? Okay. It's doing something. Oh, it's printing true. No, sorry, what? It's not what I want. How come it gets? Where did that come from? Maybe like the neighbor. Oh. Remove. Oh. That remove obviously returns a boolean. So really we want to do this. And then this, and then let's try it again. Okay, and we've got an order of letters, and how do I know if it worked or not? Okay, let's just print and do some print line, print out debugging. Here we go. So every time we reduce the temperature, let's print the solution that's currently have, and we'll print the temperature as well. So the temperature going down, that. And this solution is not changing at all, which is strange. Let's print the cost of the current solution. So do this temperature space old cost. Okay. And the cost is staying pretty constant as well. The solution is not changing as well. So why are we not? So not changing anything right now. So here's where it change to a new solution. And when the temperature is fairly high, there should be a good chance that it's going to change. It should change even if the new solution is a really terrible one. When the temperature is high, it makes me think. Now, what's this cost? 983. That's not. It should be something 1 over. What's this? Divide by 1. Let's just divide it by 1. No, let's invert it. Okay. It's changing. It's changing, and the. I feel like I'm in the Matrix. It's going up and down, and it should, when the temperature gets low, it shouldn't ever go to a higher cost. But here, look at that, it jumps to a higher cost. So, why is it doing that? So that makes me think this can't be finding an optimal solution. If it just right at the end, it's going up and down on these. So what I want to do is I'll just look in. So in Dartpad, I'm going to see what's going on with the thingammy. What's this acceptance probability? Okay. Okay. So E is from the math thing. Okay. And old cost. Let's just grab old cost. So let's say it's going to from this one. So it's going from this one and it's jumping up. Sorry. Yeah. Let's do Control Shift C. And it's jumping. The cost is jumping up to this one. Here. And the temperature is quite low. Stop it. And we end up with a number that is, let's raise the temperature a little bit. Oh, that's like almost certain probability that it will go to a worse solution at this temperature, which is not actually very high, in my opinion. So it makes me think maybe these numbers actually need to be something more like this. Oh, now that's a very small number. Look at that. So when the temperature goes up a bit more, this number gets more realistic. And then when the temperature is at 0.1, it's gonna. This is a small difference. So it's going to. Let's look. I think I need to have my costs come out a bit more, not so tiny. So it looks like all the costs have three zeros after the decimal point. So what I'm just going to do is times them by 1,000. Let's see, let's make this big. And right, there is no spoon. Neo, you're the one. So it looks like it's finding a. It was changing a lot, and then it settled down, and it's not changing so much, just a little bit, and then it's not changing. I think that's what's supposed to happen. So the cost was like haywire up here when the temperature was higher, and then it goes to 9 to 2 to 9. 2, 3, 2, 4, 2, 4, 2, 6, 2, 5, 2, 2, 2, 2, 2, 0, 2, 2, 2, 0, 2, 0, 2, 2, 0, 2, and 1, 9, 1, 9, okay, 2, 0, 1, 9, 1, 8, 1, 9, 8, 1, 9, 8. And it stopped there. And so I think this solution is probably a pretty good one. And I think this is simulated annealing, and let's run it again. Just for the matrix effect. And that's interesting. It looks very similar, quite similar there to the previous one. You want us to compare? No, it's just so. Now what I want to do is output the words that go with those, that when you learn that letter, what words can you now read and write, and then when you learn the next letter, what can you read and write for the output. So you could do something similar to the cost function. So let's put this with a new line, and line separated with an extra line. Then we want to just put some underscores, something. Then we want to do is add the letters. The letter here. Then do this. This one is print the word dot to word tab. Word dot Roman word tab. And then we'll put a thing, and finally dot English class. Run it again. Will you take the red pill or the blue pill? Oh no. Sorry. All words. Okay. Mr. Anderson, you seem to be leading two lives. No, hang on a minute. No, I don't want to get all of them. No. I want to get the new ones. Okay, now I'm just gonna, this is the last thing I'm doing, and I don't use output anywhere else. So I'm just gonna make it edit this all words list. So after I print the words that match, I'm going to remove them. Now I can't remove the word here because this for loop is using an iterator across all words, and I can't, while it's inside the for loop, I can't edit all words. But after the for loop, I will remove all the words. I use this remove where thing, and it takes the element word W and W and letters learnt contains. Okay. Doing the annealing again, Mr. Anderson. And this is it. This is what I wanted. So the first letter, you don't get any words. The second one, you don't get any words. But then the third one, you start getting words. Ata, it's grandfather. And then you learn this letter, U. Uta, uta. Why don't, now hang on a minute. This, why did you not learn this one after this one? Because you could get uta in before that, and that would be a better solution. Man. Okay, hang on. One thing I can do is just increase the amount of time it spends on each temperature iteration by putting this up to say 500. Let's go. Okay. It's a slow matrix. The temperature is going down, 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 down. And you see the cost getting better solutions, cost going down gradually, and up and down. So the end is changing here. I wonder if my neighboring thing is not good. I really should be able to swap. What have we got here? Yeah, I've got the same solution. Okay, so that didn't help. I think this one, just moving one at random and sticking on the end, is not a good neighbor. Not a good neighbor. We'd rather swap them. But I can't with the queue. We should be using lists all along. Okay. Well, if I put this back down, let's put 200. It doesn't take too long to run, so I think I can just expend the expenditure of having a so we're going to bump the element up. So what I'll do is I'll so what I'll do is this. I will remove it. No. So what I'm going to do is I'm going to go in the index, bong, so what I'm going to do is I'm going to transfer one by one the letters from this queue into this queue, and when I hit the index I'm going to hold that letter and let it go one letter. Okay. And so I'm just going to do the standard for loop for this job. And if I equals, say, index, right, we want to say hold. hold equals if I okay, here we go. We get the element that we're shifting. Okay, then we go through the elements. If we're not at the index, we simply put the simply add the next one in. If we are at the index, we don't add that one in. We skip it. Okay. And then if we are at the next, after the next one, so we've done then we add that letter in, then okay. We got a range error on line 78. Okay. Nothing's changing again. But man, it's so close yet so far. Okay, I'm just trying and test this so I should get this queue with an element swapped in it. Why can I run that? Now what? Oh. Now I end up with all B's. So solution okay. Let's see what's going on. Three D, we take the D. 1 D. If I is not equal to index, add solution element at I. A B C D E F A B A C. Oh, A swap. Okay, it's B, so B is swapped with C. A, C, B, D, E, F, G. Thank you. Okay, and we're going again. We're getting a score. Temperature's going down. Cost is going down, mostly 194. Okay, this is possibly good. Okay, awa ka. I think this looks good. Ended up with a fairly low cost. Awa ka na nga u da. Okay, let's try it one more time. Okay, this is similar and good as well. and equals 194. Okay, I think we've done it. I'm satisfied. We have done simulated annealing, and we've solved the problem. In fact, Dart is a new language. It's not widely used yet, and simulated annealing is not a particularly turn-to solution, in my opinion. Maybe I am the first person to write a simulated annealing algorithm in Dart. Who knows? I could be making history, and you could be watching it being made. Thank you for coming on this adventure with me, and we've finished a project in Dart, and I have learnt some Dart from scratch, and you have watched me learn some. Now I want to learn some more. I want to do a web app. I've got an idea in mind. I don't know if I'll ever have the time to put together a video and make it, but it would be very useful if it was made. I've wanted it to be made for a long time. I'm not telling you what it is, sorry. Hopefully I'll be able to make it, and then you'll know, and make a video. This is I'm Toby, and thank you for watching.